For over 140 years, every single power plant on Earth has worked the same basic way. Coal plants, gas plants, even nuclear plants. It does not matter what heats the water. The last step has always been the same. You boil water into steam. The steam blasts through a giant spinning wheel called a turbine. The turbine spins a generator. Electricity comes out. That is it. That is the whole trick behind almost every light bulb, phone charger, and refrigerator on the planet. And here is the part that should genuinely bother you. That idea is older than the car, older than the airplane, older than antibiotics. It was locked in back when people rode horses to work and a telegram was the fastest way to send a message. Engineers have spent well over 100 years trying to squeeze more power out of that same steam trick. They built turbine blades out of metal grown one crystal at a time. They pushed temperatures and pressures higher than almost anything else humans build. And after all of that effort, all that money, all those decades of genius-level engineering, the average power plant in the United States still wastes about 60% of the energy it burns, more than half. Gone. It leaks out as heat into the sky, into rivers, into the air around cooling towers. You pay for the fuel, you burn the fuel, and more than half of it just disappears without ever turning into usable power. Engineers have known about this problem for generations, not as some small annoyance, but as one of the biggest puzzles in all of engineering. For over 60 years, some of the smartest people in the world searched for something to replace steam, a different fluid, a smarter design, something that could grab more of that wasted heat before it escaped into the sky forever. They kept landing on the same surprising answer. And in December of 2025, in a steel factory in a mountain city in southwest China that almost nobody outside the country has ever heard of, that answer quietly switched on for the very first time in human history. What happened there, and what has happened since, might be the biggest shakeup to how we make electricity in over a century. And by the end of this video, you are going to understand exactly how a machine that runs on the same gas you breathe out could end up changing how the entire world makes power. Before we get into it, if you have ever wondered why your electric bill keeps climbing even though power plants keep getting more efficient, this video is going to answer that in a way that actually makes sense. Hit subscribe now, because we are about to show you the exact machine, how it works, and why almost nobody saw this coming. Section 2. The weird trick. Hiding in your own breath. To understand why this new machine is such a big deal, you need to learn about something strange that most people never hear about in school. You probably learned that matter has 3 states: solid, liquid, and gas, ice, water, and steam. 3 neat little boxes. Simple. But there is a secret 4th state. It only shows up under very specific conditions of heat and pressure, and when a substance hits it, something genuinely bizarre happens. The line between liquid and gas just disappears. The two turn into one single thing at the same time. Scientists call this a supercritical state. Here is a simple way to picture it. A liquid is heavy and thick. It stays in whatever container you pour it into, and it does not spread out on its own. A gas is the opposite. It is light, it spreads everywhere, and it fills up any space you give it. They are basically opposites. But once you cross into the supercritical zone, a substance becomes both at the same time. It gets thick and heavy like a liquid, but it flows and spreads easily like a gas. It is not a trick of the eye either. Scientists can watch it happen in a lab. Heat and squeeze a sealed tank of a gas past a certain point, and the visible line between the liquid part and the gas part just vanishes. One fluid, no border. Now here is where carbon dioxide, the same gas sitting in your lungs right now, becomes the star of the story. To turn water into a supercritical state, you need brutal conditions. You have to heat it past 374 degrees Celsius and squeeze it to a pressure roughly 220 times higher than the air around you. That is an incredibly harsh environment. It chews through equipment. It needs special expensive metals just to survive without breaking. That harshness is a huge part of why advanced power plants cost so much to build and keep running. Carbon dioxide is nowhere near that dramatic. It reaches its supercritical state at just 31 degrees Celsius. That is a warm day at the beach. The pressure needed is still real, but it is far, far gentler than what water demands. Getting CO2 into this strange in-between state is, compared to water, almost shockingly easy. And once CO2 crosses that line, it turns into the perfect fuel for spinning a turbine. It becomes almost as heavy and dense as liquid water, but it still flows through pipes with the ease of a gas. That combination matters more than you might think. Here is the simple rule behind every turbine ever built. The more mass you can push through the spinning blades every second, the more power you get out. Steam is light and fluffy compared to this. To get real power out of steam, you need giant pipes, giant blades, and turbine halls the size of aircraft hangars. All that size exists just to make up for the fact that steam does not carry much weight per gallon. Supercritical CO2 is so dense that you can push a massive amount of mass through a machine that is tiny by comparison. Engineers at a research lab in Texas have said that a desk-sized supercritical CO2 turbine could theoretically power around 10,000 homes. A desk, not a warehouse. Not a football field-sized turbine hall. A desk, and the efficiency gap is not small either. A well-built supercritical CO2 system can turn over 50% of its heat into usable electricity. The best steam systems running in the real world today usually land somewhere around 35 to 40%. That is not a small upgrade. That is a completely different level of performance. Here is the part that will really surprise you. None of this is brand new science. The basic engine cycle behind this technology was written down all the way back in 1872. Scientists were seriously testing CO2-based power ideas back in the late 1960s. The idea has been sitting on a shelf for over half a century, fully understood, just waiting for someone to actually build it. So why did it take until the end of 2025 for anyone on Earth to make it work in the real world? To understand that, we need to look at exactly what stood in the way. Section 3. Why nobody could build it for 60 years. Building a working supercritical CO2 power machine is not like building a slightly better version of something old. It is one of the hardest engineering puzzles of the last 60 years, and 3 separate walls have stopped almost everyone who tried to climb them. The first wall is heat-destroying metal. To get the best performance out of this system, the CO2 needs to be heated to around 700 degrees Celsius before it hits the turbine. At that kind of heat, most metals start to slowly change shape, even under pressures that seem steady. This slow bending is called creep. A metal bolt sitting at 700 degrees does not stay exactly the same length forever. Over months, it very slowly stretches. In a machine spinning at incredible speed under crushing pressure, even a tiny shift in shape can be the difference between a smooth-running system and a disaster. On top of that, hot CO2 actually attacks certain metals at a microscopic level, sneaking carbon into the metal and making it brittle over time. A blade that starts out tough and bendable can slowly turn fragile while spinning thousands of times a minute. Engineers had to invent brand new metal blends just to survive this double attack from heat and chemistry. Those special metals cost far more than regular steel, and because nothing has run for 20 or 30 years yet, nobody could promise investors exactly how long they would last. No promise meant no funding. No funding meant slow progress. The second wall is even stranger. One of the biggest reasons this system beats steam is that it recycles its own leftover heat. Before the CO2 even reaches the main heat source, the system grabs warmth from CO2 that has already done its job and feeds that heat back in. Think of it like reheating your coffee, using the warmth still sitting inside the empty cup you just drank from. This trick is a huge part of why the system is so efficient. But making it work means passing enormous amounts of heat through an incredibly thin wall while both sides sit under pressure roughly equal to what you would feel 2,000 meters under the ocean. To pull this off, engineers had to carve tiny channels, some thinner than a human hair, into stacks of metal plates, then fuse millions of these channels together into one solid block. The result works beautifully, but there is a catch. Once it is built, you cannot open it up to check on it. You cannot repair it from the inside. If a tiny crack ever forms deep inside that block while it sits under crushing pressure, it does not fail gently. It fails suddenly and violently. Proving that these blocks could survive decades without a single hidden flaw took engineers years of testing. The third wall is speed. Because supercritical CO2 is so dense, the turbine itself can be tiny. That sounds like a pure win, but it comes with a trade-off. A smaller turbine has to spin much, much faster to pull the same amount of power out of the fluid rushing through it. A car engine cruising on the highway spins at roughly 2,000 to 3,000 times a minute. These turbines can spin 10 times faster than that or more. At those speeds, ordinary bearings, the parts that let a shaft spin smoothly, simply cannot survive. The friction alone would cook them within hours. Engineers had to build entirely new kinds of bearings. Some float the spinning shaft using magnets with no physical contact at all. Others float it on a paper-thin cushion of the CO2 itself. Both ideas work in a controlled lab. But nobody had proven they could survive years of non-stop, real-world, no excuses operation. 3 walls, metal that fights back, a heat recycler you can never open up, and a turbine that has to spin faster than almost anything else humans build. All 3 had to be solved at the same time, in the same machine, and then kept working every single hour of every single day. That is exactly why this technology sat fully understood on paper for over 50 years, while nobody could actually build it. Here is where it gets interesting, because someone finally did. Section 4. The day it finally turned on the city is called Liupanshui. It sits in the mountains of Guizhou province in southwest China. It is the kind of heavy industrial city built around coal and steel that most people outside the country would scroll right past on a map. China's Nuclear Power Institute had actually been quietly chipping away at this exact problem since 2009. They got a stable version running inside a lab back in 2019. Construction on a real, full-sized version began in 2023. Then, on December 20th, 2025, after 16 years of work, something switched on inside a steel plant there that had never existed anywhere on Earth before. It was named Guizhou 1, and it became the very first commercially operating, grid-connected, supercritical CO2 power system in history. The location was not picked by accident. Steel plants have a process called sintering, where powdered iron ore gets superheated and fused together before it goes into the furnace. That process throws off huge amounts of blazing hot exhaust gas. For decades, that heat was simply cleaned of pollution and vented straight into the sky. Free energy, paid for by fuel the plant had already burned, disappearing every single day. Guizhou 1 catches that heat before it escapes. The scorching exhaust gas flows through a heat exchanger, warming up a stream of CO2 until it crosses into that strange supercritical state. The CO2 then blasts through the turbine at incredible speed, spinning the generator and making real electricity. Then it loops back around, cools down, and does it all again. The results that came out of it were stunning. Compared to the older steam-based systems steel plants normally use to catch waste heat, Guizhou 1 produced over 85% more power generation efficiency. Net electricity output jumped by more than 50%. And it did all of this while taking up half the floor space of the old equipment. Over a full year, the plant generates an extra 70 million kilowatt hours of electricity from heat that used to just vanish into the air. That is roughly enough to power around 6,000 average American homes for an entire year. Created from waste heat, the factory was already producing anyway and had been throwing away for years. Now it is fair to stay a little cautious here. The detailed engineering numbers behind KO-10-1 have mostly come from the company that built it and from Chinese state media, and they have not yet gone through independent outside review. A healthy amount of skepticism about the exact headline numbers is reasonable. But here is the thing that does not change, no matter how skeptical you are. The machine is real. It sits inside a working steel plant that cannot afford to fake results, because that plant has to ship real products on real deadlines every single day. And this part is where the story gets even more interesting, because the update since then has been just as big as the original launch. For the first 5 months, engineers ran the plant with just one unit online, watching every single number closely to see if it could survive real, sustained industrial punishment. It did. All of its performance numbers met or beat their targets the entire time. Then, on May 30th, 2026, engineers connected a second identical unit to the power grid. With both units now running side by side, the site reached its full planned output of 30 megawatts, officially becoming the largest and most advanced supercritical CO2 power plant running anywhere in the world today. Think about what that really means. This was not a science fair demonstration that ran for a few exciting hours and then got quietly dismantled. This is a machine that has now been proving itself day after day inside a real factory for months in a row. According to estimates shared alongside the project, if this same technology were rolled out across China's entire steel industry, the fuel savings would be roughly equal to the output of an entire large coal mine, while cutting carbon emissions by more than 12.8 million tons every single year, from one industry, in one country, using heat that used to just float away into the sky. Section 5. Where this goes next. The steel plant in Guizhou was never meant to be the finish line. It was chosen as the safest possible place to prove this technology could survive in the real world. If something small goes wrong at a steel plant, the factory just earns a little less bonus electricity that day. No city loses power. No hospital goes dark. That is exactly the smart, careful way to introduce a brand new kind of machine into the world. And now that it has proven itself, the plan is already moving toward much bigger targets. The most exciting one might be nuclear power. Right now, nuclear plants make electricity the exact same way coal plants do. They boil water, make steam, and spin a giant turbine, which means they need the same massive turbine halls and the same enormous cooling systems. Swap that steam system for a supercritical CO2 system instead, and the same amount of power could come out of a plant that is dramatically smaller and cheaper to build. That matters enormously for a newer idea called small modular reactors, compact nuclear plants that could be small enough to power a single town or a remote area that could never afford a traditional giant reactor. Pairing that idea with this new turbine technology could put nuclear power within reach of places that have never been able to consider it before. Shipping is another huge target. Nearly everything you own crossed an ocean at some point on a massive cargo ship, and those ships burn enormous amounts of fuel every single day. A supercritical CO2 system does not just run more efficiently, it also takes up far less space, which is incredibly valuable on a ship where every square foot matters. Early research testing this idea on nuclear-powered ships found efficiency gains approaching 49% compared to advanced steam systems already in use today. Then there is solar power, but not the panels on your roof. This is a different kind called concentrated solar power, where huge fields of mirrors focus sunlight onto a single point to create intense heat. Places like the desert areas of the Middle East, North Africa, and the American Southwest have incredible sunlight, but they are also usually very short on water, and traditional steam-based solar plants need a lot of water to run. Supercritical CO, two systems can run a closed loop that needs dramatically less water, which could open up huge sun-soaked regions of the planet to serious solar power in a way that was never realistic before. And then there is the nearest term opportunity of all, which is simply capturing waste heat everywhere else it exists. Steel plants were just the beginning. Cement factories, glass factories, chemical plants, aluminum smelters, and oil refineries all throw off enormous amounts of heat as a byproduct of what they already do. Almost all of that heat currently just leaks into the sky. If even a fraction of it could be captured using machines like this one, the impact on global energy costs and carbon emissions would not be some tiny rounding error. It would be a meaningful slice of the entire world's industrial energy use, recovered from a process that was already happening anyway. China is not the only country racing toward this. Research groups in the United States, Germany, South Korea, and Japan are all working on their own versions, including a large pilot project at a research institute in San Antonio, Texas. But China was the first to move this technology out of the lab and into a real grid-connected, commercially operating power plant. And every single day that plant keeps running, it collects data that no laboratory experiment could ever produce. Data about how the metal holds up under real strain. Data about how the bearings behave after months of non-stop spinning. Data about how the whole system handles the unpredictable swings of a real factory. That data feeds directly into the next version, and the version after that, and the version after that. This is exactly how big technology shifts have always worked. They look completely flat and boring for years, right up until the moment they suddenly are not. The steam turbine did not change the world the instant it was invented, back in 1884. It changed the world once it had been proven reliable enough, cheap enough, and trustworthy enough to be used everywhere, on every ship and in every factory. That took decades of real-world running time to earn. Supercritical CO2 turbines are only just beginning that same climb. But for the first time in over 60 years of trying, that climb is finally underway in the real world, not just on paper. So here is the question worth sitting with. The steam age lasted 140 years. A brand new machine running on the same gas sitting in your lungs right now just proved it can beat it. If this technology keeps scaling the way it has in just the last 6 months, which industry do you think changes first? Nuclear power, cargo shipping, or something nobody is even talking about yet? Drop your answer in the comments. I read every single one. If this kind of story is the kind of thing you want more of, do me a favor and hit like, subscribe, and turn on notifications so you do not miss the next one. We dig into breakthroughs like this the moment they happen, long before anyone else is even talking about them.